We are ready.
Okay, good morning once again. The topic of today's last lecture will be the random matrix limit of QCD. And when I say QCD, I really mean that we have, I mean QCD in a bit more general sense, so I will allow for a fixed number of colors, including let's say 2 or 3. We could also call 2-color QCD, and we will have a fixed number of flavors. And typically, people take only the light flavors, so 2, 3. And this will also be a fixed number. Now, when I say that there's a limit in which QCD becomes a matrix model, this of course should tell you that, well, this is a very modest attempt. We will not solve QCD with a random matrix model. QCD is a quantum field theory, strongly interacting, that there's an area where it is non-perturbative, an area where you can do perturbation theory, and of course we will not cover all this with a simple model that you will see, even if we maybe add a few more details for structure. So what we can hope at best is that in some limit this description will work. And I will explain more, of course, where this little corner is. So it will be very low energy and we will see how it goes. So the steps I want to take is first we'll massage a bit QCD so that it is in the form that we can do a replacement. Then, in the second step, I will do a naive replacement of the QCD partition function by a random matrix model. And that was introduced first by Jacques Barscott and Edward Churiak in 1992-93. And I want to do that already then, because then you see how this relates to what we have been doing. Of course, I could also have done the non-historic order and do the precise limit before, but I decided for pedagogical reasons not to do so. So the precise limit, I may already say now, will be from QCD to go to an effective low energy field theory that is a series, so this is an effective field theory for Goldstone bosons, because we will be dealing with the region where we have Goldstone modes, because we have a broken global symmetry. Now this is still a field theory, and this goes under the name of chiral perturbation theory, and the Goldstone bosons will be typically pions or more mesons if you consider more than 2 flavors. And then, on top of that, you have to do another limit, and that is called the epsilon regime, and I will explain what that means. And in this regime, we will find that the chiral Lagrangian and the whole theory will collapse to a random matrix model description. Now, even though I said we will not solve QCD, of course not, but I would still like to emphasize that it's remarkable that even in a tiny corner of a strongly interacting quantum field theory, we can compute something analytically, non-perturbed. And I showed you the plots in the first lecture where you saw lattice simulations of QCD. This is really first principle, knowing nothing about random matrices, just putting your fermions on a lattice, having a QCD action, computing correlation functions as you would do it for physical observable. And you find, yes, with these analytical curves, and maybe I will show 1 or 2 how to derive them if there's time, we get in perfect agreement. So this is, I think, quite a remarkable thing. Okay, so let's start with QCD. So, of course, we have QCD, we will not call that the partition function, we will call it the path integral, or the fermions and gauge fields. And everything I will do in Euclidean 4-dimensional space-time. And the reason is not only because we want to, at the end, compare with lattice simulations, but the other reason is symmetry. Because in 4 dimensions, the gamma matrices have a definite symmetry. I mean, in Lorentzian signature, one is Hermitian, the others are anti-Hermitian. In 4-dimensional Euclidean, they are all Hermitian, and then the Dirac operator has also Hermiticity properties. And we will need that, because these are the symmetry ingredients we need for building our model. So we have an action, so long I here. So we have so the Freudian plus Ml. Okay, and they are what you think they are. So mu is this plus trace F mu, where F is the field strength tensor, non-abelian. Normally you would expand that in terms of the generators of SU(n)2 or SU3. I don't need to do that. I will just write that schematically. I will massage a little bit more the fermionic sector. So this will be for NF flavors looking as follows. Well, of course, the Dirac operator is a covariant derivative dressed with gamma matrices. We should not forget that it depends on A. Okay, so for every flavor we have a different mass, we have a different kinetic term, and I would like to write this as a big spinor with a big mass matrix M, because I will need that later. So M is just the diagonal of block mass. So in flavor 1, 2, and okay. Now, as you know from your quantum field theory course, if you want to consistently quantize fermions, you have to use anti-commutation relations for the creation and annihilation operators. So, so we need Grassmann variables, and I mean, probably know all this, but because it's early in the morning, let me just recall. So let's say we have a couple of them, A1 and N. They anti-commute, so xk L is 0. And then we have, we can define an integration over them with these rules. And of course, higher order terms will vanish. So, so that implies that, well, let me go straight away to the example with 2 Grassmann variables. Let's say we take 2 convex Grassmann variables. So, star. And then if you write the following expression, where A has bosonic entries, so these are all bosonic. So when I say bosonic, I mean they commute. And the Grassmann variables anti-commute, so they are fermionic. And if you would expand the exponential function up to 2nd order, which you can all do, multiply everything out, use these rules, and also use, of course, that let's say psi anti-commutes with the differentials. What you will get is AD minus BC. And that's just the determinant of A. Okay? I think this we may have very well seen already, and of course this also holds for arbitrary n. And I would also like to remind you that if you had such a bosonic integral, then first of all, the sign here would definitely matter if the integral exists. For the Grassmann integration, it doesn't matter if you put here plus or minus. If I call this a Gaussian integral. So if you have then d2n x e to the minus x transposed a x star, this would give you up to vectors of pi 1 over z. Okay. So with supernatural units, as I learned, I can set pi to 1, and then also maybe factor of 2, I can set to 1. Anyway, so this will give you an inverse determinant, and here, of course, the sign is important. Okay, so going back, I'm just saying that because basically we want to integrate out the fermions formally. Now, of course, the fermions will depend on space-time. So either you discretize and then you get a finite set and then you can apply these rules, or you are happy with a more formal object that we get as follows. So we now formally integrate our fermions. Minus h. Okay. So far nothing has happened. This is of course to be understood in a formal sense. This is a differential operator, and if I have to then explain, as I tried, what is meant by the determinant of the differential operator, and then of course I still have the path integral about gauge fields, and this explicitly depends on the gauge fields. We can even push that further and diagonalize this operator formally, and we will do that in a moment. Now I want to make another extension of TCP that is adding a topological term, pi times integral for x trace f mu dual to the action. And I want to have a parameter here. Let's call it theta. Theta should be an angle. And it turns out that, again, up to factors of 4 pi, this topological term is given by a number. That's the winding number. So mu is typically this term is called theta vacuum. But I don't want to think about it as really something physical. It's really, as you will see, it will be a device to do a Fourier transformation of the specific partition function. Now, so far so good. So here and before I was talking about Dirac operator. So what is the relation? The relation is given by an index theory. Yeah, index theory. And that tells that mu is not only one thing number, but it is equivalent to mu. Well, the same mu counts the number of 0 modes of the Dirac. Now this is a bit sloppy. In fact, what it is, it's the difference between the left and the right-handed 0 modes. And I will introduce what left and right-handed is also in a moment. But before doing that, let me write down what we have now. So what we have is, well, this can be any integer, and we will later restrict ourselves to positive mu. So I can now write this partition function of path integral in the following fashion. So now I sum over all the different winding numbers. I will now have a Dirac operator here that has a fixed number of 0 eigenvalues. That b slash of a plus mf e to the minus standard Young-Mills action. The rest has been absorbed. So this has a fixed number of 0 nodes. Okay. So I can also say that this defines just the topological sector into the I theta mu z nu. Okay, so z nu is this whole thing. Okay, so before I will continue and make a statement about how to replace this by a random matrix model, let me tell a little bit about further properties of QCD. So far, we have not done anything related to random matrices. So another topic that we will need is chiral symmetry breaking. So I'm sure you have seen that in your quantum field theory lecture, but it's good to remind ourselves. So for the Euclidean, the gamma mu's are Hermitian. Then I will choose a chiral basis for the gamma matrices. So I can write gamma 5 in this way. There are, of course, other representations. And then I can define projection operators PL R, so P left or right, as follows. 1 plus minus gamma 5. So that will just project on the upper sector or on the lower sector. And of course, because they are projection operators, if you square them, they give the same. And then PL, PR, P0, such as PR, PL, and PR plus PL. Okay. So with that, we can define left and right-handed modes just by taking this big spinner here and writing this PL plus PR on the side and define side L plus side right. Okay. Now, let's look at the action here. So what are the symmetries of this action under global rotations? Well, there are the following properties. First of all, we will use it slash gamma 5 anti-commute. And this actually implies, if you look at this matrix here, you can easily convince yourself that in order to have a matrix, of course in a formal sense, I mean, this is an infinite dimensional operator that I can represent as an infinite dimensional matrix, but we can also truncate it by going to the left, for example. So in a formal sense, the Dirac operator will have to have this block structure. Okay, and you can easily convince yourself that if you multiply this with this, this will give minus a b. And then if you do it the other way around, you get minus b. Okay, so the sum is 0. Now there's another ingredient that follows from this, and that is that the Dirac operator is anti-Hermitian. So that also tells us something about the symmetry. So anti-Hermitian means, okay, I could do that with a minus, I can also do that with an I, so this matrix has to be the conjugate of this, so let's call it A was a bad name because A is the gauge field. So the Dirk operator is of this structure. That already looks like what we have been doing for random matrices, but so far this is the QCD Dirk operator, because this is not a finite dimensional matrix. Now, I was talking about symmetries, so the symmetries go as follows. So we have a mass term and we have a kinetic term, and those have different symmetries. So, kinetic term. So if you write that out using this definition, you get the following composition. So this is invariant under a global rotation. Where you independently rotate the left and the right. Side of R and U and F matrices, constant matrices. Okay, so and this is true for three colors or more in the fundamental representation. So the symmetry is U left and F times U right and F. Okay. For two colors, for example, the symmetry is enhanced actually to U2, but I will not explain that. I will give some reference for this, and also I will come to the edge one later. Okay, so this is the symmetry of the kinetic term. And what about the mass term? For the mass term, we have that left and right mix, so the symmetry will be broken. Okay, and so in the best case that we can possibly have, we still have a global symmetry, namely when so this is still invariant under UL. Right. So so the mass term breaks this symmetry down to a single element. Okay. Now, this is maybe not surprising, but the reason why we analyze this is that in QCD, at low energy, there is an order parameter of symmetry breaking, and that is the chiral condensate, that we call sigma. So that's the absolute value of the vacuum expectation value of psi bar psi. And normally this should be 0 with all the equation and annihilation operators inserted. However, this is non-zero. So let me write this out. And this is non-zero. So this is called spontaneous And you see that this vacuum expectation value breaks Carrel symmetry from the bigger group to a smaller group in exactly the same way as the mass term. Okay. Now, so if you were familiar with condensed matter physics, but most of you are particle physicists, you will also see a parallel to this when you have a Hamiltonian of a ferromagnet that is typically rotational invariant, but the ground state will be magnetized, so it picks the magnetization in one direction, and that is your magnetization is the order parameter. But you can also break the symmetry by adding external magnetic field. And the role of the mass term is exactly like the role of the external magnetic field. So what people often do is they actually add a small magnetic field and then remove it at the end of the day. And we will also do that here. If we want to test Carrel symmetry breaking, we will first have a mass term, and then we take the limit n goes to 0, and this is called Carrel limit. And then you see if Carrel symmetry is broken, the order parameter will stay on 0, and if it's restored, then it is 0. And you also know that for the ferromagnet, there's a phase diagram, and so we have one for QCD, although this is not yet very well understood. So there's a chemical potential for quarks, and there's a temperature, and then there's a region where the order parameter is non-zero, and then there's some phase transitions here. So this is the cartoon you normally see when you look at this kind of literature. So outside the order parameter is 0. And this is the low energy region, so low temperature, low density. This is the world where we live on, where quarks and gluons condense to hadrons and mesons. And this is where QCD is difficult, when this phase is difficult. Okay. Up here, when, for example, high temperature, you can do perturbation theory. Here, you cannot. And we will basically look at the vicinity of this point, which is, of course, the 1.5 point. So,
sorry, the different regions, I don't know if I just missed that. What are the other transitions there? What is the order of the transitions there?
Okay, it is conjecture that, okay, here for the nuclear matter transition, it is established that the transition is first order. And here we have critical temperature. Now, the critical temperature has been established by lattice simulations. And the order is thought to be second order when the masses are 0. When the masses are non-zero, this will be a crossover. So if it's second order, you'll be a tri-critical point, and otherwise you have a standard critical point. And this is under heavy debate between different groups. We had simulations. People have made progress. They've done Taylor expansions here in this direction, close to the temperature axis, because when you add mu, slash plus mu gamma naught, I have to put a gamma naught because chemical potential couples to psi dagger psi, okay, not psi bar psi. And this operator is not, it's neither Hermitian nor anti-Hermitian. So this is so plus or minus. And that means that you get a phase in your QCD action if you add here the potential. And that is very bad if you want to do standard Monte Carlo simulations, because Monte Carlo means that you discretize your quantum field theory, put it on a lattice, and then you generate configurations, and the importance or weight of the configuration is given by, well, this probability. But this is only probability if it's a positive number between 0 and 1. If it has a complex phase, you're lost. Now, there are many ways people have tried to go around this problem, but it does not really have been solved. Now I could also tell you how to solve random matrices once we get there, including chemical potentials. This is possible, and it's possible very well in this area here. So that's again another advantage of random matrices, and maybe just one word. The way you solve it, well, you go into the complex plane, this has complex eigenvalues, and you use orthogonal polynomials in the complex plane. And then you compute the density. That is no longer an object that is positive, it's a density that is as a real and imaginary part, and that may become negative, because you insert a data function here into something that is not positive. But this can be discussed. Okay, so that was a little detour. Now, this symmetry breaking pattern, so this is typically called a vector symmetry, is a little bit more subtle. So there's a people call that a theorem of Buffer and Witten, where they show that vector symmetries will be unbroken, but there's also an anomaly. So in fact, if you write this as U1 A S U L S U L times U1 vector, then this is one vector times SU vector. Okay. So this is the symmetry breaking pattern that really occurs. So U1 is broken by an anomaly, so by quantum effects that break the classical symmetries. I just erased the SU2 case. There are 3 different chiral symmetry breaking patterns. This is one pattern, and if you want to know more about this, you should look in some older work by Michael Keskin from 80. Yeah, I will give them later. So, chiral symmetry breaking patterns. So let's call it KSD patterns. And reference is also free archive. And it will turn out that these 3 different symmetry classes will exactly correspond to the 3 symmetry classes of Dirac operators in random matrix series. Of course, I will have to explain that a bit more. So this will correspond to the 3 classes of Dirac operators beta equals 1, 2, 4. And this one here is the one for beta equals 2. I will have to make the link more precise, but this will come. Okay. Now, as I promised, as a second step, I will do a naive replacement of this QCD partition function as we have it here by a random matrix model. Now, you can already almost guess how this will look like. Well, I had a Dirac operator here. I remember that has this block structure. So, the random matrix theory will look as follows. We will replace the Dirac operator by a random Dirac operator in the Young-Mills action by some average over these random fields. Okay? As I said, this is not the end of the story, but this is how the story started. So, the Dirac operator will look as follows. I'm W dagger, we have flavor, and we have e to the minus trace and trace. Actually, you could put here anything and you would expect that this is more complicated, but because of universality, that was conjectured at the time, they choose the Gaussian representation. And now W is an n times n plus new matrix, so it has new zero modes. So it will correspond to this sector here where we have a fixed number of zero modes. So maybe I should call this RMT to distinguish from the QCD case. And these matrix elements will be complex, so we are in the beta equals 2 class, and that is thought to be corresponding to this symmetry breaking pattern here. So if I drop out the U's, we just have this pattern. Okay. I will explain that, how that will relate in a moment. So now in the random matrix model, we can of course just go to eigenvalues. So you see already that this is a bit more complicated than the models we were dealing with, where we just had here a gauge. So we have added a bit more structure, but this will be possible. So this will give following thing k from 1 to n, 1 k plus nf square. Now what I do also to make life simpler is that I said that the Dirac operator in QCD, and of course this naive random matrix Dirac operator, is anti-Hermitian, so it has eigenvalues on the imaginary axis. But I don't want to twist my head. And
So in
yes,
the last line, lambda k
plus mf square. I mean,
sure.
so in the end, the lambda k are the eigenvalues of W dagger, and the Dirac eigenvalues are, we would call them xk plus or minus lambda k. So they are of course positive. So these are the Dirac eigenvalues. They come in pairs. Okay. And as I also said, I mean the eigenvalues of, so D is minus the dagger. So the eigenvalues are purely imaginary and they come in pairs mirrored around the origin. But because I don't want to draw imaginary eigenvalues all the time, I will draw real ones. Okay, so we just wrote it. But this is true. Okay. So I said if we diagonalize this, we get this product here. So taking into account the Jacobian, we will get Z nu RMT is a constant times integral from 0 to infinity from 1 to n. And I will say what n is in a moment. Then we had lambda I to the nu because we have zero modes. Then we have product f from 1 to nf. Lambda I plus square, and then we have an nf to the nu and e minus lambda I times lambda mod with lambda square. Okay. Now we're back to what we know. Now what is n? So n is the number of eigenvalues. I mean, if I would think again about this matrix here, so actually we have 2n plus nu eigenvalues. So nu are 0 and then n come in pairs. And this corresponds to thinking about Dirac operator on a lattice. Volume V, and then well, V would just label the number of eigenvalues. Okay, and let me write again. NC is 3 or 4 or 5, 6. So NC, number of colors, has nothing to do with the number of eigenvalues. The number of eigenvalues will go to infinity if we want to make a continuum limit. Okay. Now, before going on, I would like to show, better to say, I would like to apply what we learned yesterday, how we would solve this random matrix model. I will be very sketchy here, but just to give you an idea, because now we have this in the partition function, and before we only had nf equals 0, this got quenched, which we solved with like F polynomials. So I think it's nice to see how we apply what we did yesterday, and then I will continue with the map of why this is really related to QCD in a certain limit. So far, we just do heuristics. Okay, we say we have the same symmetries, block off diagonal, and then we hope that we get something out, but this can be made more precise. So, solution of R3. So let's look at the first 0 number of flavors. This is also called quenched QCD. Now, in this quenched case, this Dirac determinant is absent, so we can solve that using Laguerre polynomials. So, or pk of lambda just minus k factorial to make Laguerre polynomials monic. Okay, and then we can go put that into the kernel, compute our correlation functions, and then take the larger limit. Now, what about unquenched? And by the way, you should not think that this is a weird approximation. That's the approximation people doing LSQCD did all the time in the beginning when they didn't have so much computer power to compute eigenvalues of the determinant of the Dirac operator. In the quenched approximation, you get actually quite good approximation to the real particle spectrum. But we want to do unquenched. So now we have a weight which is lambda nu, and then the product here 1 to nf lambda minus nf square e to the minus lambda. Now, as I told you, for arbitrary weights, we have the following representation. Pn of lambda is given by the determinant of an expectation value of this kind. Now, of course, this expectation value is with a full weight. Okay? This I proved. Now, you can, of course, think that this is again a determinant. So let's look at nf equals to 1, or let's first write the general thing. So we can write that as that lambda minus n dagger, and then we can write here product 1 to nf, nf squared plus w dagger. And now this is, of course, the quenched average. And here in the average, we have the expectation of this times this, divided by the partition function, which only contains this. So, nf squared plus w dagger. So when I say Q quenched, I mean quenched average is just with this way. Okay? This we know. Now let's take nf equals to 1 for a simple start. So then we know that, well, we just have here, I forgot one determinant, but of course the determinant, the product is the product of the determinants. Okay, so nf equals 1, we have one determinant here, one determinant here. That's a kernel, and this is a polynomial. So Pn of lambda just up to some factor, which I write down. I'm not mistaken, we should so now everything is determined. This is now the kernel of the quenched polynomials, and this is the quenched polynomial. So we know the polynomials, we can do the kernel, we can do the correlation. Okay. And this can also be done for nf greater than 1, and if you want to have a reference on the archive, th 97.1123 by the Damgar and Ishigaki. However, this story is actually much older. That you can really, if you look at classical results of orthogonal polynomials, already in the book of Segue, you will find once you know the polynomials for a weight function W, you can also construct the polynomials for the linear factor times the weight, which is exactly what we do. So for nf equals 1, we know the weight without nf, and then we look what is the weight times the linear factor. And that is already in Segue. Okay, so now I told you how to solve the matrix model using orthogonal polynomials. We didn't do the limit yet, but this will come. So we can compute the density, two-part function, etc. of this random matrix model 0. Now you will ask, well, okay, I gave all this picture, current symmetry breaking, order parameter. What does this have to do with the Dirac operator? Okay, yes, please.
General question, because I'm not sure. So this with this you can compute in principle the partition function, but
and density correlation functions.
Between eigenvalues, though, I mean the space-time correlators.
I can compute correlation functions of eigenvalues. Yes.
Right, but like correlators of space-time correlations, because we got rid of the dependence of space-time.
Yes. Yes. This will have to come. But I mean, this, as I said, this is a naive replacement, and I will have to explain why this is not so naive. So at the moment, this is, of course, this is a zero-dimensional model.
Okay, but okay.
It will come.
Yeah, sorry.
So what is the relation, say, density of Dirac operator eigenvalues and the answer is the Banks-Kesher relation. And that states that sigma is the density of the Dirac operator eigenvalues at zero momentum divided by the volume. So we go on a finite volume, and then this density will tell us if we have a symmetry breaking or not.
Okay, so there is a problem.
This?
Well, the 0 over 2, what is the first?
That's just pi.
Okay.
Just the number pi times the density at zero momentum. Of course, I will have to say what is the density of the Dirac operator. This is the QCD Dirac operator. Okay. Banks and Kesher knew nothing about random matrices. This is a QCD relation, and I will show you how this follows in a moment. So let's take nf equals 1. So let's put the determinant back upstairs. So upstairs we have psi bar d slash plus m psi bar. So if you differentiate with respect to m, this will bring a psi bar upside down in front of the exponent. Okay, so you can generate the condensate, so the vacuum expectation value, let me drop the absolute values, as a logarithmic derivative of the QCD partition function. Okay. Now, on the other hand, we could also take the QCD partition function as we had with the determinant. We can even formally diagonalize the QCD Dirac operator, so we would have then dm log an integral dA, etc. and then we have real QCD eigenvalues that are labeled by some k, m u x k plus m squared, and then we have Young-limits. Now, if we take the logarithmic derivative here, what we will get is the following average: k 2m xk squared plus m squared. Now, this is a QCD average. Okay, and I neglected the derivative with respect to m to the u, but this will go away.
Sorry, are you sure that is sigma not sigma to square?
Yes, it's just sigma. I mean, we just have dm.
Sigma is the chemical
No.
What is sigma?
Sigma is the expectation of the sum of time. Okay, and this you bring down by.
Okay, so dimension. Okay, so dimension 3 in mass, right?
Yes, yes.
So rho, the dimension of rho is one is m, right? So you have m, and then the volume is m3, right? Is 1 over m3. So I'm not sure
about the dimension. I think the dimension should
rho,
match.
what is the dimension of rho?
Well, the integral over rho should give 1. So it should be, well, you can see it here. I mean, if you replace this, okay, so this has dimension 1 over m. And then I think it should come out.
Yes, right.
Okay.
Maybe, yes.
So I already have taken the next step. I have taken the volume to infinity. Of course, this expectation value here in QCD is only meaningful when I do a regularization. So both UV and infrared regularization. So one way to do it is to put things on a finite volume and on a lattice. Okay. Otherwise, this expectation value will diverge and I will have to renormalize, etc. But I mean, this is not an argument. Now, you see that, I hope you still remember, this thing here, when m goes to 0, will give a delta function. In fact, pi times the delta function, and I forgot the volume. To normalize the density. Do you see that? So 2m over x squared plus m squared, m going to 0, it's a Lorentzian representation of the delta function. So if first taking the volume to infinity, and then m going to infinity, n going to 0, I get pi times rho at 0 divided by the volume. So this is the Banks-Cash relation. So all I had to do is I had to regularize my QCD objects, but no random matrix model so far. So what we learn here is that, yes, we have a relation between the Dirac operator spectrum and this non-perturbative order parameter of private symmetry breaking. And we also learn that it's the small eigenvalues that are responsible for this condensation. And what we also learn is that these small eigenvalues really behave differently from eigenvalues. So if you would have a free theory, then your eigenvalues would just go, well, the eigenvalues of the Dirac operator are momenta, okay? And the momenta in the free theory just go like 1 over L, okay? If you just put them in a box, you quantize, this is how they go. But here, they go like 1 over volume. Because, I mean, so the spacing is like density at the origin, and that goes like 1 over volume. So, different from free eigenvalues, and it will also tell us that we will have to scale we have to rescale v or n times x squared, we call it x. So n goes to infinity and x goes to 0. So we are zooming into the origin in our random matrix model and also in our QCD. So going back here, what that would mean is that I would have to split the limit n goes to infinity of L and mu x squared over n, and that can be shown as just the Bessel function. So the polynomials will become Bessel functions, the density will become a bilinear of Bessel functions in the random matrix model. And then you can plot the Bessel density, plot lattice simulations, and they will agree at least for the smallest eigenvalues. Okay. So I would like to now take the next step and explain this naive random matrix ansatz, why this really works. Okay. So this is our random matrix theory. And now we want to understand why does that work. And I didn't show pictures again, but okay, you can believe it. And people doing lattice simulations, they were first quite puzzled actually. Why such a naive ansatz with a random matrix model will describe their smallest eigenvalues? So they wanted to see a field theoretical reason why this works. So this hard unit is going to QCD to an effective field theory called current perturbation theory, and then going to random matrix model. I will verify this relation for the partition function and give you an argument how you would see that also for density correlation functions. So we have a breaking of global symmetry. So for example, SU in F times SU and F SU in F. So if you have a global symmetry that's broke, you get Goldstone bosons. Okay? And what are the Goldstone bosons? They are the lightest particles. In QCD, they are not really, they would be zero mass if all the quark masses would be zero, but of course in nature they are a little bit above zero, so the Goldstone bosons are light but not zero mass. So for two flavors, these are just 3 points. Okay. Now there are two other current symmetry breaking patterns which are in the notes. I will not write them down. So this pattern is for 3 colors in fundamental. So what do the Goldstone bosons do? They live in the Goldstone manifold. So we will have to parameterize u of x in the coset space. Because things are so simple and when you can divide our 1 SUN, so to speak. And the U will be something like given by generators, then there's some conventions here, which is part. And then the psi for 2 flavors will be expanded in terms of Pauli matrices. Okay. So these are emission fields. This gives a unitary matrix that is a representation of SUN. Okay. Now, what is the effective action for the Goldstone bosons? Well, in principle, what you would have to do is you would take all the particle spectrum, integrate out all particles, except the Goldstone bosons. Of course, this is very difficult to do. So in practice, what people do is they write what is called the chiral Lagrangian. Based on symmetry principles. So let me write down. So this is chiral representation theory. This looks as follows. And then some convention, and I will say a few words in a moment. So this is the kinetic term, and then we have a mass term. Probably missing a half here. Yes. U of x plus u then of x. And the path integral, this is still a fully interacting quantum field theory. So you will have a path integral over these u fields, and then you have e to the minus d for x L calculus. And what I've written down for you here is just the two leading order terms. So this is leading order. And in principle, there would be higher order terms, so in terms of u squared, du squared, du, u squared, etc. So it's an infinite series of terms, and only the leading order term, when we expand this thing here, you will see that the leading order term will produce here the kinetic term for the primates, and also will produce the mass term for the primates. But there are many higher order terms. So it's a non-linear, non-renormalizable field theory, but this is not a surprise. I mean, effective field theory is not supposed to be renormalizable. This is effective field theory. So, for principle, one could go, and people do that, of course, and expand this to a certain order, compute correlation functions between pion fields. Okay. Now, I did not say what this is. So this is the pion decay constant, and it turns out that this is, after some massage, the chiral condensate. So these are what is called, so these are low energy constants. And they don't follow from QCD. You have to compute them, let's say, using lattice simulation, and these are only the leading order ones. I mean, once you have higher order terms, there will be more. They're called L6, L7, L8, etc. Okay. So this is quite a complicated field theory. I would like to point at one thing, namely when you put here the when you put here the expansion in psi, you will get here psi squared over s pi squared. So these are the masses, but remember n are the quark masses, and this can be argued using a Spurian technique. So you get a relation between the pion masses, and I believe it should look like this. Okay. So in your first principle simulation, you put quarks on the lattice and you have gluons. So what the parameters are the quark masses. But at the end of the day, what you want to get are pion masses. So in order to relate them, just doing this comparison, you will need to know these low energy constants. This is, by the way, called Gernot-Renner relation. Okay, one Renner. Okay. So we are not yet at the random matrix model. Okay. Yes.
Is it obvious, or do you explain why sigma? That constant is a chiral.
No, no, I didn't explain that. I mean, but you normally you put a parameter b here, and then you can argue and see why this is a condensate. You have to go to a level of correlation functions to identify this. Okay. But I mean, I just
for us, phi is more obvious, right? You
yes,
redefine the
decay constant
of
the pions. Yes, yeah. Yes, indeed. Okay, but I mean, up to this. I think it should be clear. Okay, so What is the random matrix mode limit? Now, there are two limits you can do. When you are in a finite volume, A to the 4. The first limit is the physical limit you would like to have. That's not the random matrix mode limit. And that is the limit when L is larger than 1 over m pi, which is the Compton wavelength of the pions. That is what you normally would like to have. You would like to have that these some pions fit in your box that you can do physics. Okay? And the counting here is that we count momenta. So when I say momenta now, I mean momenta of the pion fields. Okay, so we put here the leading order determinant term, and then of course that came from CF pi, and then you go to Fourier basis, so you have p squared plus n squared, just normal. Okay, so n pi they are counted like 1 over L. So if you look at then this theory here, and if you look at the fluctuations of your path integral in Fourier space, you will get that you will get fluctuations of the order. So this gives a volume, this gives a t square n square, then you have to integrate of bosonic field, so you get a 1 over. So you have 1 over d times t square plus n square. So this is order v, this is order 1 over L square. So this is of the order 1 over L square. So these are small fluctuations. Now, there's a second limit. And the second limit is an unphysical limit. And that was introduced by Gernot and Leutwiler. In 1983, 84, 85. Again, they didn't know anything about the matrices. You will see the reason why they introduced this limit. So this limit has the opposite quality. So in principle, so the pion wavelength is larger than the box. It's unphysical, but never mind. So what happens then? So here we will count m pi is 1 over L squared. Okay? Then you can make this work. Right? L squared larger than L. So what happens now to this here? So, and of course, P will still count like 1 over L because always in perturbation theory, that's around field theory. Now for non-zero modes, this is unchanged. So we have order 1 over L squared fluctuations, but for P equals 0, let's look at it. So we have order 1 over volume times m pi squared. Okay. These are the fluctuations of the zero modes. Now this is of order 1. Because this is 1 over L square, so this is L4, 1 over 1. So we have to treat P0 modes non-perturbative. So the way we do that is we just reconsider our expansion here. So this has, of course, propagating modes p equal non-zero and non-propagating modes p equal 0. So what are the non-propagating modes? They're just constant modes. Okay. So what we do is we parameterize the following. So u of x is now u naught times e to the I psi of x a sigma a, and then the pi's and etc. Okay. Now this thing we are not allowed to use perturbation theory. Okay, so we are not allowed to expand to leading order, etc. We have to keep that. So how does the current Lagrangian look like? And I should say this was called epsilon with u. And epsilon is called 1 over L, and that's confusing because there are other epsilon regimes and other theories, like in finite matter. So this is called epsilon current perturbation theory. The reason why Gasser and Leutwiler introduced this is that in this limit, the leading order becomes exact. So all higher order terms are suppressed. So we only get this to leading order xi and this. So let me write this down. So we have xi now p non-zero modes, e to the minus e4x, d mu xi, d mu xi. And then we have this integral, which is now group integral over constant su and f. And then we have x of v times sigma v, because the modes are constant, so the integral here just gives volume. Over 2 over trace m u naught plus u naught back. Okay. So we have a Gaussian free theory, and we have some group integral. This is the limit that is equivalent to the random matrix model. Now, we don't see it maybe yet, but this is what it is. So we have a factorization. So the propagating modes decouple, and I mean there are 3 propagating modes, just as a constant in the partition function, so to speak, and the non-trivial information is contained in this group integral. Now, in order to convince you that this actually does agree with the random matrix model, I will have to take a limit of the partition function in the random matrix model and show that it agrees with this. The random matrix model will not give you this. Okay. So this is our next task. Well, before that, we have to do one more step. But before doing this step, I would like to make one more statement. So epsilon equals chiral random matrix theory. So this was leading order, and I will show you how this works. Now, what we did here was just a tree-level argument. Okay, we replaced everything by fields. Now, we could, of course, also take higher order terms and then do a one-loop computation. Okay, so that would bring here higher order terms, xi cubed, xi 4. We will then have to bring them down, contract them with theory, use the finite volume propagator, and get a one-loop calculation. Okay, now the statement is I'm not doing that. The one-loop calculation preserves this factorization. So we still have this correspondence, and epsilon phi pt is RMT. This we normalize as pi and sigma. So they will become f pi effective, and that will contain corrections from the one-loop calculation. But other than that, everything here will be the same. So we will get just sigma effective and f pi if we would couple it to f pi, which we don't to this order. Okay. So in order to show that the random matrix partition function is equal to this group integral, I have to do one more massage. Now, this is an SUN integral, and so far we have said nothing about Dirac operator eigenvalues, and we have not specified them to have a fixed number of zero modes. Now, of course, that will also raise the question, this is a chiral Lagrangian. This can compute pion scattering. How can we relate this to Dirac? So this will be another question I have to answer. Yes, please.
From the point of view of like comparison with like this limit on lattice setup, be a limit in which a correlation function is more or less as big as, or even smaller than, even bigger than the box, right?
Yes.
I want to say that the correlation length
Yes.
So that's very far from the continuum limit.
Yes, but you can now go on the lattice to this unphysical limit, use the random matrix model correspondence to determine these parameters sigma and f prime. They are the infinite volume parameters. Okay.
Yeah.
So we will have to scale mass times volume times sigma. So this is a constant, but other than that, the low energy constants are the infinite volume ones. And if I do one loop corrections, then I get the one loop corrected ones. So I fit these low energy constants in an unphysical limit, and they are what they are. And then I go with my lattice simulation to a physical regime and use these low energy constants. And you should see this Banks-Kesher relation, which was here, that rho of 0 is proportional to sigma. And the density at the origin oscillates a lot. And now we have to fit this with a constant to determine sigma. Okay. In the random matrix plot, you know how this function analytically depends on sigma. So you can make much better fit than using this rough, just having some very noisy signal that we put a constant through. Okay. So I said we have to fix the number of zero modes. So if you remember in our vector QCD, we had the theta term mu and z e to the I theta mu. And then we had this integral here, blah, 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 f mu. Okay, so I can now combine this with the mass. So that will give me an e to the I theta term here. So then I can project on this get mu by doing the Fourier transformation. So this is 1 over 2 pi integral 0 2 pi d theta e to the minus I theta, and then the partition function with e to the I theta over nf times the masses. Okay. Now for this, I take this limit. Okay, so I get, so let's put that here schematically. So this is 3 times SUNF integral. And then this SUNF integral with this integral will give you the UNF integral, and this phase here together with U0 will give you UN matrix. And that is the integral we are calculating now. And this is maybe a bit quick, but I want to be precise, this has to be done. So what I want to show now is that this integral and epsilon pi pt leaving out this free series, so just taking this and now integrating over full unit in the group. U0 UNF e to the 1/2 trace that this is equal to the limit n goes to infinity of RMT. So let's first compute this integral. Well, I will not compute it, I will give you the answer, but I will give you a reference. This is a very nice unitary group integral that actually comes out as follows. Minus 1 with m x is m times d times sigma. So d goes to infinity, m goes to 0, so that this is constant, and I absorb this to write a little bit less, but otherwise this is the dependence. And then I get a vector function here. And plus b minus 1 n x divided by 1/1 of the n hat squares. This is the answer. And to see that, well, either you go back to the first paper where this was done in paper by Brouwer, Rossi, and Tan in 1981, Brouwer, Rossi, and Tan. Then this was again calculated by Leutwiler and Slüger, so the same Leutwiler. But there's also a very nice derivation, not only of this group integral over unitary groups, but over other integrals, like the Hare-Chandra x-square integral, which is an important identity in many problems, and that you can find derived using an expansion in group characters in this paper. 7161. So that's a possible source of derivation. Okay, now we claim that this is equal to the random matrix model partition function in this limit. Now let me do that for an example. Limit equals to 2. So the limit so the partition function is just the expectation value. Now just this is factor here. Okay, now this you can express through the kernel. The kernel you can write with Laguerre polynomials. The Laguerre polynomials you can scale. And what you need, so what you will get is the following, using Christoffel Darboux, some constant. Okay, with the limit we have to take, and 1 and 2. Christoffel Darboux has a denominator. And then we have L n minus m1 square, and minus 1 square minus the 1 exchange. Okay. This we have calculated for. Okay. It's all done. So you just need to open a book on asymptotics of classical orthogonal polynomials, for example, Kratzstein, and then you will find that using m1 or 2 hat is 4n n1 or 2 square, and using the following limit, n goes to infinity. Okay. I don't put the right factors in. So what you get from Radstein is this. N mu x minus x over n is x to the minus mu. Now you see that in the larger limit, these two terms will be equal, so you have to Taylor expand one, so you have to use a derivative of the Bessel function. So this is the modified Bessel function of second kind. You get a I here because you have a minus, so you get a square root of -1 that goes from normally in Radstein you find the asymptotic with a plus, and you get j, and from the minus you get I. And then you need this identity here. Of course, this term will cancel in the difference. This limit here will become this result. this is equal to that. Okay. So now in doing this limit here, this was basically the kernel of minus n squared minus 2 squared. So I should also give you the limit for the density. So because we have here minuses, that will disappear. So since this is a quantity, I would like to write down.
So Kn is the kernel, right?
Kn is the kernel, yes. And the kernel was the expectation value of two characteristic polynomials. Okay. And you also know that the following is true. So, in kernel GUP, we have the density of lambda. Now let's go to various squares. So lambda is x squared, which is x hat squared over n. So this is down of lambda and lambda. Okay, this is just the one-point function. And if we now take a larger limit with this scaling, basically using the same result here, you get rather than n's, you get lambda 1, lambda 2. Then you have to take a limit, of course, that this becomes equal, but I mean then so you get 0 divided by 0. So basically you have to do one more expansion. And then what you get at the end of the day is that for the limit of this density of x hat, this is called best kernel and the best density. So this is rho mu int of x hat, and that is x hat over 2 j mu square of x hat minus j mu plus 1 x hat and mu minus 1. So this is the universal density. It's universal because we get the same answer if we don't take a Gaussian, but if we take an arbitrary potential. This required some heavy work, but this has been done, so this is universal. Now if you plot this will look as follows. So we are really zooming into the origin here, right? Because we take n times x squared x hat. So this goes to infinity, and this goes to 0. So what we really do is we have this finite and semicircle for the Laguerre ensemble. If you plot that as Laguerre polynomials, it would look like this. Now we zoom into these oscillations here, and the density looks like this. This would be like 0. Now the average of this density will be in principle sigma, but we have done things on the scale of sigma, so this will be a constant. So this is like effective parasymmetry is broken, and the average density is constant. And if you now plot lattice data, they will follow this curve quite nicely. But of course, the beta quantity is to define the smallest eigenvalue, which can also be done. I don't think I will have time to derive that. So let me just write down the quantity. So this is P first eigenvalue moved equal to 0. And that is just into the minus x square over 4. And if you take Mathematica, you put your equal to 0. 0. Around this, you see that this will very nicely follow the curve. And for the lattice people, of course, this is a much better object to compare with because it's finite. It's normalizable to 1, so you don't have any. You don't have these strong oscillations. So fitting this object to your lattice data, you can extract signal. Okay. And you see how simple it is. This is 0 eigenvalue QCD in this particular limit. Okay, now I still have some time. So there's one thing, maybe your questions, yes.
The value of sigma, like in terms of energy, is this lambda QCD scale. So.
I think it's something like 250, and then in cube units. Of course, it's an order parameter, so it's not physical. But I mean, if you do the simulation, this is what you get. The lambda QCD, if you like, is the scale of energies that you have neglected. It's actually not lambda QCD, but it is the mass of the first non-Goldson boson. So if we only take pions, it will be the row. So starting from the row, all this will not work. I mean,
which should be.
What should be?
It's the only scale that comes up, right? And lambda QCD should.
It is also order of lambda QCD, but I mean, it's not lambda QCD. I mean, we do current perturbation theory, and that only works if the non-Goldson bosons don't contribute. And the first non-Goldson boson in this counting for two flavors is the row. So when the row starts interacting, this approach breaks down. Other questions at the moment? Okay, so there's still something that maybe you don't understand, and you are perfectly right not to understand because this was puzzling. So let's look at this object here. So what we have shown is that this partition function here, at least for two flavors, I've done the calculation explicitly, and I've given you the result for the group integral. So I mean, there's some gaps, but these can be filled. So we've shown that the level of partition functions is a non-trivial part of epsilon current perturbation theory and random matrix theory in the larger limit degree. Okay. Now. Then I went ahead and said, aha, very nice, now we can do orthogonal polynomials, compute the density. But you may ask, hang on, I mean, if the partition functions agree, why should the densities agree? I mean, or the two-point function, or this individual eigenvalue? So, or put even more fundamentally, this is a theory of pions. What do the pions know about Dirac operators? What do they know about Dirac operator eigenvalues? How can we see that? So this was a question that was answered by several people, and in order to do that, well, we just need two simple identities, or maybe three. So the first identity is the following. So you can write that as t to the base a. So if you take the derivative of that z minus h, well, what will you get? You will get, you put this up, you get the log gives a 1 over, so you get a trace of 1 over z minus h, and then you still get the z minus h. So why am I writing this down? Well, I'm writing this down because what we want to do is we want to generate resolvents in the current perturbation series. And the way to do that will be with what the way how quark determinants couple to the current Lagrangian. That we know. This is how they couple. I mean, if we add one more quark, we have a larger group, we have one more mass here. Okay? So the idea will be, let's generate resolvents. So I'm now doing chiral perturbation theory without random matrices, just to understand how to get the density. So I will introduce extra source quarks, if you like, to generate resolvents, and then for the resolvent, of course, this will be our Dirac operator. Okay. So let's put it. Never mind. Yeah, then it's true. So we get the resolvent, and then from the resolvent, you know, we just take the imaginary part, the discontinuity, and that will give us this density. But we don't want this extra source. We only want the resolvent. So we have to remove it. And there are two ways to remove it. And the first way goes under the name of replicas. So what do? Well, you take the following limit. So you can address that with 1 over n. So we take the limit. This is 1 over n. I'm now writing the matrix expression, but n is 0 of yes, dz 1 over n determined to the power n z minus h. Okay, so when you take the derivative, you get one factor of n that will kill that factor. So you get then 1 times trace 1 over z minus h, and then you get still that to the n z minus h. And then when n goes to 0, this will go to 1. Okay? So what does this amount to? Well, it amounts to know this. For nf plus u flavors. That you will say, okay, I gave you the integral over u and f, arbitrary nf, so also nf plus n. So that was a Bessel determinant. But then we have to take n to 0. Okay, so we have to analytically continue. Now that's always a problem with replicas, because suppose you have a function, you know it only for the integers, then you add plus sine n pi. It's always 0 when n is integer, but when n is a real variable, it's not. Now there's a way to fix this, that was observed, I think, by Jacques Berber's thought again, and you can look in this review. So that's 5, 2, 29, and that is a review anyway on this whole topic, QCD, random matrix limit of QCD. The reason why one can do that is that these group integrals, they enjoy a relation to integrable systems. In particular, there's a relation to the polar lattice hierarchy. So let me write this equation because it's nice. So it holds that f mu of x, okay, x is now the determinant mass, square equal to constant times x squared z and then plus 1 x z and then minus 1. And this integrable hierarchy helps you to do the analytical information. Well, I think it's also nice because it's nice to see that there's another relation between random matrices, or in this case, this current dimension and integrability. There's another way to do this. So here we would then have to compute u and f plus n. Okay. And this procedure has been done for the density. Okay, because otherwise we need to generate 2 resolvers, and then we have n plus m, you have 2 radical limits. This is complicated. Nobody has done that. And of course, the people doing Dennis H theory, they were very happy to see at least that this density comes out, because I mean, then they were confident you can also do things without knowing random matrices at all. Just take the epsilon regime, the replica limit, and you get this density without knowing about random matrices. So that means that this equivalence is really working for the density for higher order. This was work my PhD student Francesco Basile and I did, but I will not quote it. I will just quote the idea for the very simplest resolvent. So one trick I said is replicas, and the other trick is supersymmetry. So how does that go? Write the resolvent as 1 over n j. J is the source. Then z plus j minus h divided by z minus h when j is 0. So you differentiate the first guy, that will generate a trace, but the determinant will stay, and then you set j to 0, and then the two determinants cancel. Okay? So now what do we have to do? Well, these are bosonic quarks. They will couple here, but well, we then need the supergroup interface. So for this. Okay, if you want the K-point function, you have to compute this supergroup interface. That's quite tough, and then nobody has done that explicitly except for k equals 2. And for arbitrary k, Francesco used an idea that's called superpositionization to directly map the generating function. These are generating functions for resolvents and hence for density. And he managed to map these to the generating function in the random matrix model. Okay, so now you have an idea how one could also compute density and correlation functions of the Dirac operator, even in a theory that is talking only about ions. Okay? So we have understood now the equivalence between the random matrix model limit and its current Lagrangian, also for density correlation functions. Now I think the last minutes I would like to spend just to say some closing remarks of what I didn't do and what is interesting. So if you have any questions to QCD, please ask now. Yes?
There is. So in QCD at low energy, one can study also, in particular on the lattice, one can study also the effective string, so Wilson loops, basically.
Yes.
So that is an effective string description, which is the somewhere surfaces, which is not topological though, because both those bosons interact, etc. So is there a matrix model way of tackling that problem? Like it looks a bit like 2D gravity, but it's not topological.
I don't know. I would have to look at this. I was thinking you were asking about parent correlation function. Of course, that you can also compute, but then this is dynamics. This is again. 4-dimensional quantum field theory, and then the only thing random matrix models help you to do is to get this low energy constants. This, of course, people have done.
Sorry,
yes.
This approach you can create also more general Lagrangian with all the Fermions, the mesons like Joan Lasino model, something like this.
So
for instance, you can also treat something like a neutron star. Because in a neutron star you have to consider also mesons or kind of things.
Okay, so you could take certainly more flavors. That's what I indicated. I mean, of course, the difference between the NJL model and the Carrel-Lagrangian is that, and I think the Carrel-Lagrangian you can really derive from first principles, doing a strong coupling expansion. Some people from Rome have done this, and I don't think the NJL model is such a close link from first principles to QCD. But of course, you can use it as an effective field theory and calculate things. And people have done that. as many other models. And for high density,
this is not an application.
no,
derive Joanna Lasigno Lagrange.
no, not that I know. But of course, what you say about neutron stars is of course very interesting. But then we need the density. I mean, we need the chemical potential, and of course,
because
yes.
in viscosity, the problem, if I get it, I'm not an expert.
Yes,
so
yes.
To track a neutron star is that there is a chemical potential inside a neutron star. So if you want to treat dark matter in phase diagram,
Yes.
with low temperature and very high density, this is the problem. Right?
Yes, indeed.
The chemical potential.
Yes.
So people consider some phases like sphere or
Yes.
block.
Yes, indeed. I mean, this is
So my question, my question is if in this problem this approach can help or not. What is the status?
Yes, understand. So, as I said, you can study when the matrix model plus the chemical potential, and you can still solve it. However, that is a model, if you like, the phase diagram, still close to the axis. So actually, you will scale u square times n times the volume. Now, what you were asking in are investigating, of course, are other phases here. Okay. Now, there are few papers by Thilo Wettig and co-workers where they also have a kind of random matrix model or effective field theory model in this spirit at very high density. So then you get, depending what you look at, you get some Cooper pairs and you get some BCF as type of structure. You have a gap and it replaces a Carrier condensate. So people have studied this a little bit, but this has not been exploited so much. And of course, the problem is you can do effective field theory, but you will always like to test your ideas versus that. So that is the status at least I know so far. And that's why also these phases here are still okay. Maybe people agree more than I think. I'm not an expert on this either, but there's definitely still an open question. Okay, so maybe one more word about other relations. So what I didn't talk about multi-matrix models. So this would be of the type DH1, DH2 minus n trace D1 plus D2 H2 minus H1 for example. So this would be a two-matrix model, and these can be solved also using orthogonal polynomials, and these enjoy the property that they can really serve as a model for a much more conformal field series. I didn't talk about many more ideas of matrix models. For example, you have seen already, this is like a unitary matrix model, okay? And people have studied this. So now the eigenvalues align the circle, and then you have some potential. People have studied models, with orthogonal symmetry, so these kind of things can be done. Maybe a reference here is in our handbook, in chapter 15 is about multi-matrix models, and 17 is about unitary matrix models. But there are, of course, other models. I didn't talk much about the relation between random matrix theory and algebraic geometry. Some of you like fancy surfaces and moduli spaces, etc. So in this original paper that I quoted by Jan Amjan and William Chekhov, they have already a section on matrix models used to compute intersection numbers of modular spaces. There's more recent work by that far now, for example, if you are if you want to look into these things. I gave already a reference to this review by Marcus Marinho, where he also talks about inside ones and matrix models. Maybe you want to learn about this as well, because you followed Francisco's lecture. I should also, last but not least, say that people have, of course, thought, can we do matrix models in larger than 0 dimensions? Because everything here has been stacked. Now, there's not so much actually about 1 dimension, so you add time basically. I think you should look into the original paper by Bazin, Parisi, Itzig, and Zuber, which is in CMP 59, just because it's a classic. I mean, it's from 1978, and so this is a very important paper in both quantum field theory and matrix models, and they have a chapter on matrix quantum mechanics, where you have at least 1 dimension. I think there's also some recent development where you look at tensor models, thinking that these are models for higher dimensions, but my time is over. So I thank you for your attention, and I hope you will enjoy the next 2 weeks.